Let's do one more parallel axis theorem problem. Here we want to find the moment of inertia about this point here. In an earlier video, we used the definition of moment of inertia. We performed an integration, and we came up with this result that the moment of inertia about that point was 7/48 ml squared. That was when we used the definition of the moment of inertia, which you might recall goes something like that. It was a little bit of work to do. Let's see if we can get the same result by using the parallel axis theorem. The parallel axis theorem is that the moment of inertia about some non-center of mass axis is equal to the moment of inertia about the center of mass axis plus md squared, where d is the distance between these two axes. The moment of inertia about the center for a uniform rod is, and we derived this in an earlier video as well, is equal to 1/12 the mass of the rod times its length squared. And in this case, the center of mass obviously is right there, and this distance right there, that's d. Because there's the center of mass axis, and here's our new axis. So that's d right there, which in this case is what? L/4. So that means that this term here becomes m L/4 squared. All right, well, what does this come out to then? This is 1/12 ml squared, and this is 1/16 ml squared. What's the common denominator? I think it's 48. So this would be 4/48, and this would be 3/48. Look at that, 7/48 right there, just like what we got last time. Now to do that, what you need is you need this value right here, which you can typically find in a table of moments of inertia. Without that, you're in deep trouble. But for uniform objects, that's usually a pretty easy equation to track down out of some table. Somebody went through a lot of trouble to solve a lot of these for us already, and so we don't have to derive them all the time. We can just look them up. But look at that. We used the parallel axis theorem, and we got the same answer as if we just integrated it.